Okay, so thank you very much, and thank you for the opportunity to present our results on actuator-line simulation of wind turbines using the Lattice Boltzmann method. This is the work that is performed within the EoCoE project in collaboration of the FAU in Erlangen, which is represented by, well, me and my doctoral supervisor, Professor Ulrich Rüde, as well as our colleagues from IFP Énergie Nouvelle, Annie Ancien and Frédéric Blondel. I will start with a brief introduction to the Lattice Boltzmann method itself. I guess not everybody is aware of you, and just that we're on the same page and understand why it's useful, why it's beneficial, and why we want to use it. So in fluid dynamics, we can solve these problems with methods of different length scale. So there are the macroscopic methods that are based on the discretization of the Navier-Stokes equations. That is one end of the spectrum, and on the other end of the spectrum, we have the microscopic methods like molecular dynamics or just in general particle methods. And somewhere in between, there are the mesoscopic methods, and Lattice Boltzmann is one of them. Now, what exactly do we do with Lattice Boltzmann methods? Well, as it's a numerical method, of course, we discretize something. We discretize the space. For this, we use a Cartesian grid, so nothing super fancy. We discretize in time. For this, we use the explicit Euler method. And what is now somewhat more special for Lattice Boltzmann methods is that we also discretize in velocity space. That means we do not allow for continuous velocities, but we have a discrete set of velocities which we can represent by a so-called stencil. And the stencil, you can see an example here. This is now a D2Q9 stencil, which means two-dimensional with 9 discrete velocities. So the resting velocity in the middle and the 8 others to the corners. And for every cell and for every lattice velocity, we keep track of one particle distribution function. I will call that from now on the PDF. And the PDF is nothing more than the density of particles with a certain microscopic velocity. So instead of tracking distinct particles, we take a more statistical approach and just have a look at the probability with which particles travel into a certain direction. Of course, we can recover the macroscopic quantities like density and velocity in which we are interested in from these PDFs via the moments. So the 0th moment of the PDFs, that would be the density, the first would be the velocity, and so on and so forth. Now we have the quantity of our interest, the PDF, but what do we do with it? Lattice Boltzmann consists of 2 major steps. The first is the collision step, which is nothing else but a redistribution of particles. Of course, we do not have the particles here, but still the idea behind it is the same. So we relax the populations toward the equilibrium, which could look like something like here. So before it was out of equilibrium and now it's in equilibrium. This is done by a so-called collision operator, which is usually denoted by omega. And this collision operator is the heart of the collision step, or Lattice Boltzmann in general. So with the collision operator, we distinguish between different Lattice Boltzmann methods like single relaxation time, multi-relaxation time approaches. And it also determines the stability and the accuracy of a lattice model. What is worth mentioning here is that the collision step is usually a totally algebraic cell local operation. So we do not interact with some neighbors, but all calculations that we've done are really cell local. This will become important later. The interaction with the neighbors is then done in the 2nd step, which is the streaming step, or also the propagation step. And here, as the name would suggest, we just propagate the PDFs to the neighboring cells. So of course, the resting velocity, the PDF stays in the middle, and all others travel to their corresponding neighbors. And to which neighbors we travel is again determined by the stencil. And that's already it. That's Lattice Boltzmann in a nutshell. I will now focus a bit more on the advantages of the Lattice Boltzmann methods. Even though I've written down more now, I want to focus on 2 things. First, it's inherently mass conserving. which is a real advantage because normally for other methods, you would have to solve an additional equation to ensure mass conservation, but for Lattice Boltzmann methods, that's inherently fulfilled. So no additional equation, which of course is beneficial. And the second thing I want to point out, I already mentioned it, the heaviest computations are cell local. So the collision step, this is where the actual work needs to be done. This is a local, which means that the Lattice Boltzmann methods are very well suited for large scale applications on CPU and for GPU, because the computations are then parallelizable quite easily. That's why it's a good thing to use the Lattice Boltzmann methods for applications like we have. I will now mention or detail a bit the implementation itself. Of course, we did not use implement Lattice Boltzmann from scratch, but we're using pre-existing frameworks. The main framework is Valbala, which we developed at University of Erlangen. It's an open source framework with a strong focus on high performance computing, as well as in terms of performance, as well as scalability. What is very nice here is that we have the adaptive mesh refinement and some advanced load balancing schemes. And this is all based on the block structure domain. So of course, the mesh refinement is also block structured. What is now unique to Valbala is that we can couple it to PyStencils and LBMPy. The two of them are Python packages, which we also develop at University of Erlangen. Normally, you would use them in a standalone method, but we use them to generate code for Valbala. So now you can think the collision operator, it did not give details how it looks like, but there's a whole slew of collision operators that you could use. Same holds true for the boundary conditions, for streaming patterns, for communication patterns. And if you want to handwrite everything from scratch, do the optimization for different hardware, this is cumbersome, not feasible, and you just don't want to do that. So that's why we chose to use code generation for that. The good thing is that PyStencils and LBMPy, they have backends for CPU and for GPUs. So we don't even need to port manually to GPUs, but we can use the same abstract representation in Python and just generate our GPU code. And all code that is then generated is highly optimized. So yeah, LBMPy and PyStencils, they insert automatically vector intrinsics. They support common sub-expression elimination, so more compiler optimizations. So the code that comes out is really highly optimized. Yeah, let's come to the wind turbines actually, because this is our main application, how we implement them on top of Valbala. For the wind turbines, we use the so-called Actuator-Line model, in which the turbines are not geometrically resolved, but instead we just approximate them by the forces they apply to the flow. In the picture, you can see a scheme of the Actuator-Line method. So every blade here is represented by one actuator line. And at every point of this line, yeah, we have some routine to calculate the forces. So first, we interpolate the local density and velocity. Then we interpolate, so with that, we calculate the angle of attack, which we use then to interpolate the lift and the drag coefficients from some airfoil data that is turbine specific. And once we have all these components, we can calculate our lift and our drag forces. And we take them and just project them back onto the grid. This can be done, for example, with a Gaussian kernel, which would be the standard approach. And that's already how we implement our turbines in Valbala. It's rather simple, but we will see that it works quite well. On Lattice Boltzmann side, we chose to use the Stimulant Lattice Boltzmann method. The issue is that standard collision operators, so simple approaches like the single relaxation time, they suffer from severe numerical instabilities, especially for high Reynolds numbers. In the picture on the left, you can already see, so this is a simulation with an SRT model. And here you can see some spurious oscillations. So it was stable enough that it ran, but not stable enough to yield physical results. The cumulant lattice Boltzmann, on the other hand, so it's smooth, it's just as it should be. So it has some superior stability properties. The only drawback is that it's a bit more expensive computation-wise because it's just more complex. But using the highly optimized kernels from LBM, Pi, and Pi stencils, it's still efficient enough that we can run it in a good way. Furthermore, we exploit the mesh refinement capabilities of Valvala. So we have two approaches: the static mesh refinement, which we always use around the wind turbines. So in this picture here, you see the domain with three wind turbines, 1, 2, 3, and the mesh the refinement around them is automatically done. Optionally, we can also refine at boundaries, like it's done here, or just define some user-defined boxes when the user has some specific areas of interest that are not directly in the turbine region. Furthermore, we support dynamic mesh refinement. Here, the refinement criteria are typically based on the flow field, but the user, if they want, they can still define some custom refinement criteria that are based on something else. The bad news is currently this is only available on CPU, so we do not have mesh refinement on GPU because Valvala doesn't support it yet, but it's work in progress, and we hope that we will be able to have mesh refinement for our turbine applications on GPU as well soon. Other features that we support, we optionally can model the tower and the nacelle. For the tower, we would use an additional actuator-line. For the nacelle, we would use an actuator disk. And in the picture here, you can nicely see the influence of the nacelle being present on the wake. Also, we have tip loss models. So if the simulation is unresolved, we might not be able to resolve the tip vortices at the blades. And then it is beneficial to use a tip loss model to better predict the physics. Currently, we support the Prandtl tip loss model, or again, the user can just implement their own. As you can see in the nice animation here, dependent on the user input, we do not only support the typical horizontal axis wind turbines that I've shown you until now, but also the fancy looking vertical axis wind turbines. Now I only talked all the time about a single turbine. A single turbine is already quite cool, but of course not as cool as multiple turbines. So we are also able to simulate an entire farm. This is now a simulation of a farm with 15 wind turbines. We have some periodic inflow or periodic boundary conditions in flow direction. So everything that leaves here the domain re-enters here. And you can see very well how the wakes develop and how the turbulent structures evolve. Yeah, now pictures are nice and nice to look at. But if we want to really do physics, of course, we need some validation. For this, I will show you now some preliminary results. Everything I will show you now is based on the New Mexico test case at a wind speed of 10 meters per second. Let's jump in with the blade loads. So self-explanatory, the force distribution along the blades of the turbine. In red, you can see our implementation, Valvala. The blue dots are experiments, and orange and green are two different solvers, namely Castor and SOFA. And you see that we can, that we match the experiments, but also the other solvers quite well. So in total, this is very encouraging. I think we're doing something correctly. Of course, we're not only interested in the blade loads, but also the velocity profile. For this, I will show you just shortly where it's measured. We're looking on top of the turbine. So this is a top view. The wind comes from here. And we have some PEV, so particle image velocimetry measurements upstream, so just directly before the blades and downstream just behind the blades. And with this, we obtain some time averaged velocity distribution for the same test case again. And upstream and downstream, you can see the velocity profiles here. Again, we match very well the experimental data and the other solvers. So this looks all very good from a physical point of view. Now we do, of course, care about performance, not only physics, but also performance. So I will detail a bit the performance aspects. I already mentioned that the Lattice Boltzmann methods heavily benefit from accelerators like GPUs due to the high parallelism. The thing is, if we only ported now the LBM part to GPU, but kept the wind turbines on CPU, this would not make much sense, because in each and every time step, the turbines would have to communicate with the fields on the GPU, and this would create a super severe communication overhead and slow down the simulation quite a lot. So the natural approach is, we port the turbines also to GPU. For this, we used something that we call holistic CPU-GPU approach, which basically just means that we have only one implementation for our physical models for both CPU and for GPU. That's beneficial because that means that we only have to implement it once. So for example, the Actuator-Line model, there's only one implementation that we can use for both. And this, of course, facilitates the implementation of new physical models because you only have to implement them once. Also, it improves the maintainability because you only have to maintain one model, and it reduces model divergence, which means that we can always ensure that CPU and GPU actually do the same thing in terms of the turbines. With this approach, we ran some first tests. So in blue, you can see the normal CPU double precision test for several nodes. And in light green and dark green, you can see the GPU results for single precision and for double precision. And keep in mind, this is the very same implementation, but for the GPU approach, we directly score a lot of more M loops than for the CPU approach, even using more than 6 nodes. And here is the ratio between the simulation time and the physical time. So real time, we would be somewhere at 1. Obviously, we're not at 1 yet, but I think the trend is there. And this is actually one of our goals, to reach real-time simulation of entire wind farms in the end somewhere. For this, we have still some challenges. Even though this looks okay-ish here, the scalability is not yet ideal. So we still need to work on that, investigate a bit why the scalability isn't that good yet, and of course improve it. And in general, we just need to do more performance optimizations, because until now our focus was on the physics side. But the performance optimizations are still on the list to do. With this, I already come to our outlook and hence the future work that we want to perform. As I already mentioned, performance optimization, because we want to get close to real time, but also multi-GPU simulations would be great to further speed up the simulations and exploit more computational capacities. Currently, we only support a single GPU simulation. As I already mentioned, the mesh refinement for GPU would be great. These were now goals for the further future, and now come the goals for the further future, which are hybrid CPU-GPU simulations to exploit the entire system, and the simulation of atmospheric boundary layers, because atmospheric boundary layers are actually crucial for the realistic simulation of wind turbines and wind farms. This won't be part of the EoCoE project anymore, because it's just too time consuming for the remaining time. We hope to do it somewhere in the future then. with this, I want to thank you for your attention. And if you have any questions, I'm happy to answer them.
Thank you very much, Helen. Anyone has any question? Ulrich, it seems you've raised your hand.
Hello, I have not raised my hand, I have been clapping, but I can say a few words. So this is we should first say, Helen has been quite understating what we have accomplished. Especially I think what is very nice is this unifying approach to GPU and CPU portability through code generation. I think this is largely underestimated, and that we do not yet have full scalability running on, say, 10,000 cores or 100,000 cores even. Valbala can do that, and we should in principle be able to do that also for the wind turbines. But of course, we were only funded for a few months for Helen's work. So the funding has run out, and Helen is still here is sort of because she reports about work that she's not being paid for anymore. And I should also say a big thanks to the really excellent collaboration from our side, FAU, with our colleagues in Paris from IFPN. So that was really extremely productive, and I think that is a very good thing for EoCoE that we have this collaboration.
Okay, thank you. This is very good to hear. This is very much why this project exists. So this is great. Herbert, seems you want to jump in.
Hi, Helen. I also like your work very much. It's a lot of work. When you presented, the people from outside don't actually see it, but I know it's a lot of work. And the presentation was very nice. Just one small question. What about LES turbulence modeling? Is this kind of an implicit turbulence modeling, or do you have a real explicit turbulence model? I know that typically in the Lattice Boltzmann community, people just go like implicit LES, but now I'm seeing also people like Sago, and he's using actual explicit turbulence models.
No, so the standard approach in LBM is actually the explicit way to incorporate turbulence models, so some subgrid scale models. In our work, we mainly use the Smagorinsky model, but we also have an implementation of the whale model present. But for the results that we obtained, that was the Smagorinsky model.
Thank you very much.
You're welcome.